Hi, I'm Shai, and this is Adrian. We'll talk today on two new modules that were added to Lucene recently. Were released, I think, in 4.5. So first, let us introduce ourselves. I work at IBM Haifa Research Labs in Israel, the Information Retrieval Department. I work with Lucene for over 7 years, developing all sorts of improvements, extensions, solutions. I'm a committer. I sometimes blog when I have something interesting to say, but not too often as I should have, and feel free to reach me out for any questions that you have.
Okay. And I'm Adrien Grand. I work at Elasticsearch as a software engineer, and I'm a Lucene Solar committer as well. So that's it for me.
Okay, so the two modules are the replication module and the new index sorter. So let's start with the replicator. We'll try to split the talk half and half, and then leave some room for questions in the end. So the replicator, well, the module is all about data replication, and as I'll show later, it's not necessarily focused on index replication. So let's start with some scenarios, query load, that is imposed by the users, whether because the queries are too heavy for a single server to handle many users, or there are just too many users. Michael Bush talked earlier about 20, how many was it? 2 billion queries per day. That's probably not going to work on a single server. So one solution to the problem is to replicate the index, or actually create machine replicas, put a load balancer between the users and the servers, and then have users directed to different servers. Another scenario is a failover. You don't want to have your search application exposed to errors, maintenance issues, machines that go down. So again, you have one server. Now it can sustain the query load, but suddenly your administrator says, I have to apply an urgent security patch, and your system goes down, unavailable. So here too you want to have replicas, but you will notice that those replicas now are not necessarily active. They lie dormant until you want to bring them up to life. I just say that, of course, this scenario can be solved with load balancing as well. You just have the load balancer stop directing requests to the server that is now down. And another scenario is to take a hot backup of your index. So this was first introduced and described in Lucene in Action 2nd edition book. If you want to take a backup of your index, you can use some operating system level mechanics to do that, but that's not very good for reasons that I'm not going to elaborate. But again, now the machine isn't down. Maybe the index became corrupt. Maybe the hard disk failed. Maybe you made a change to your index schema that you want to roll back. So the solution would be to keep still one server, but several replicas of the index on the server. So Lucene replication module allows you to do any data replication. As I said, it does not necessarily focus on index replication, even though it comes pre-built with the necessary hooks to replicate your search indexes. The approach that we've implemented is a primary backup approach, where your primary node does all the indexing operations. In this case, for indexing, it does all the indexing operations, adding, deleting documents, merging segments, etc. And backup nodes replicate index changes from the primary node whenever they need to. So the update policy is totally dependent upon the application. I would just say that we saw a need for a replication module because, as you know, both Elasticsearch and Solar can do replication, and they handle failovers and load balancing already. But we did see a need for having a replication module that you can use outside the scope of Solar or Elasticsearch. For example, if you just want to take a backup of your index, you don't need to install Solar for that. Or maybe you want to have, I mean, my hope is that both Solr and Elasticsearch will one day reuse the replication module from Lucene, and we'll have just one code working. Okay, so let me describe the components that make up the replicator module. I will elaborate on them, and just keep that architecture in mind. Okay. So the replicator module is very simple. There are 4 components. Two of them are the ones that you will want to extend for doing replication if you want to replicate something different than search indices. And 2 of them are the ones that you won't necessarily want to touch because they're not doing any custom work. So a replicator is an object that mediates between clients and servers. The approach, by the way, is very similar to SVN or source control repository. You have people commit changes to the source control, and then somebody wakes up in the morning, types SVN update, and it is immediately upgraded to the latest revision. SVN does not run one revision at a time. So that's what the replicator does. It maintains a list of revisions and keeps track of which revisions are used by which clients, which revisions are currently being replicated by which clients. And when a new client comes up and says, I'm on revision X, it looks at the available revisions, and it always gives the client the latest revision, whether there are 5 revisions ahead or 100 ahead. The replicator has basically 2 implementations in Lucene. One of them is a local replicator, which you will mostly use in on the server side. That is, your indexer will do some indexing changes and then publish a new revision to the replicator, and you will probably use an HTTP replicator on the client side to replicate index changes over HTTP. The replicator is an interface which you can implement if you want to have your own replication mechanics. Revision is the one that is responsible for describing what needs to be replicated. So a revision is just a description of files. Which files comprise this revision, plus some metadata about them. The metadata is used by the clients to decide which of the files to copy. For example, the last modification date of a file, the size of a file, maybe a checksum, so that the client can decide, I have already replicated this file, I don't need to copy it again. Now, it's also responsible for ensuring that the files exist and are not deleted as long as clients replicate it. Now, when we worked on the replicator, we could choose between that approach to having the replicator do this management, for example, by opening a file handle to each of the files and ensuring that they are not deleted. For simplicity, we decided that, and especially because we in Lucene currently only offer indexing type of replication, it's very simple for a revision to ensure that files are not deleted. So when the replicator knows that no more clients replicate a certain revision, it just calls a revision.release, and then the revision knows it can release the files. As long as there are clients that are replicating, the revision will not be released. A replication client is a helper utility for the clients to interact with the replicator and pull new index, new revisions. It basically does all of the dirty work that you don't want to do yourself. It communicates with the server. It tells it, I'm on revision X, which revision do you have for me? Maybe it returns back revision X, in which case it does nothing. Or it returns in revision Y, in which case it copies the delta files to a sandbox location. And then upon successful copying of those files, it invokes the replication handler. Now the handler is the one that is responsible to act on the files. And I'll describe what the index replication handler does. But you can imagine that for example, the handler would copy the files to the index directory or whatever. Now there is a comment here. It always replicates the latest revision, so it doesn't need to replay revisions, as those are not incremental changes to the client. The index just bumped up from here to here, and you just need to get the latest view. Okay, so the replicator itself would not be very useful if we didn't offer any indexing hooks. And believe me, implementing a handler is not that trivial. So we offer two hooks, one for index replication and one for a pair of an index and taxonomy index replication. I will talk tomorrow about a facet module in which we use a sidecar taxonomy index, but for now, if you're unfamiliar with it, you can think about a suggest dictionary that you want to replicate together with your search index. So this is an example of how to replicate two data structures to have a consistent view on the client side. Okay, so what does index revision do? When you publish an index revision, it just obtains a snapshot on the index. In Lucene, there is an object that is called the index deletion policy, which is responsible for deleting commits. And snapshot deletion policy allows you to take a snapshot on the index, meaning that it takes a commit point and keeps it active, even though index writer will continuously try to delete it. It will ignore the delete requests and keep the commit files in the index. And upon releasing of the revision by the replicator, it just releases the commit point, and then snapshot deletion policy. Next time index writer asks it to delete files, it knows that this commit point is no longer needed. Now the index replication handler is the one that copies the files from the sandbox location that the client copied the files into the index directory. What it does is it copies the files and it ensures to fsync them, so that when it returns, you want to be absolutely sure that the files are on stable storage and can be searched safely by search threads. Upon any error, it rolls back the entire operation. Of course, there are a lot of delicacies in implementing such a handler. For example, you want to copy all the segments files first, but the segments _n file, which it's like a stamp on this commit point, which says which segments are in this commit point. It copies it last and it fsyncs it last, so that whatever goes wrong during the process, it can clean up after itself and leave the index directory unchanged. Now, after it's successfully completed replicating the index, it invokes a callback. It's a regular Java callback, and you can think of such a callbacks. Someone asked that on the list recently. Of a searcher manager that calls maybe refresh. So if you have on the client side your search threads, use a searcher manager to acquire and release index searchers, then you would have the replicator handler invoke that callback, which will refresh the index underneath the searcher manager, and clients, the next search thread that comes in and calls acquire will receive the new index searcher, which sees the new replicated segments. Now, implementing a handler isn't trivial. There are many traps. You want to ensure that files are fsynced, and you want to ensure that if anything goes wrong, the index directory is unchanged, or whatever you replicate is not left in a dirty state. At the moment, we didn't find a scheme for having a general replication handler which does all of that work for you. So you need to implement that yourself. I recommend, if you are using that, use Lucene's mock directory wrapper, which I think was discussed a couple of times on those conferences, because it can simulate all sorts of problems for you, like a disk crash, a disk full, random IO exceptions. So it just helps you ensure that your handler really recovers from every problem that it encounters. Now, there are similar extensions for a faceted index, so that if you need to replicate two data structures in parallel and have the searcher see a consistent view of them. If you just invoke two different clients, then you would end up with a searcher that might see one, like for example the search index updated but not the taxonomy index. So this handler works even in more subtle cases where something fails, it needs to clean up both indexes. Okay, so using the replicator is very, very trivial. At the top, you have a pointer? Yeah. At the top, you would see what you would normally do on the server side. You would fire up a local replicator, keep it open, and then whenever, for example, you commit, then your next line of code would be replicator.publish new index revision. That's how you let the replicator know that there are new files to replicate. On the client side, there are more steps that you need to take. You first start a replicator, and here it can be a local replicator or an HTTP replicator. You need to define your callback. So this is an example callback that I mentioned. It's very simple. Just call searcher manager dot maybe reopen, maybe refresh, and then you initialize the client. And the client can work in a manual mode or an automatic mode. So if you have your own logic of when you want to replicate changes, you can just call update now. If you want to replicate changes every 30 seconds, then you just invoke or start an update thread. Okay, the replicator is not done. So there are many things that can be improved. For example, currently it does not know how to resume. So if you copied 100 gigs of data and the last byte failed for some reason, it restarts the entire session. Now resuming at the session level means that if I already copied 9 out of 10 files safely, and I know that I copied them safely because I did some checksumming stuff, etc., I just copy the last file the next time I start. At the file level is more tricky. Like if we divide a file into blocks, we can do the same logic in blocks. We would just need to change some APIs of the replicator. Parallel replication, this is something that I'm always cautious about because it really depends. It depends how strong your master node is versus how many clients you want to replicate from it simultaneously. And now, if any one of them invokes replication in parallel by having separate threads replicating different files, then you want to ensure that the master node can actually sustain that network communication load. Now there are more interesting replication strategies. Here we implemented the primary backup approach, but there are peer-to-peer approaches where there is no one master node, and of course if that one goes down, then everything goes down. Where clients replicate index changes from each other. And if you think about it, if you have 100 clients replicating from one master, it's not going to work. But if one client already replicated to index revision Y, there is no reason why it cannot now be the master of that revision to other clients. Okay, so that's a future work that we want to explore. That's it on the replicator. We prefer to take questions at the end.
So thanks, Shai. I'm now going to talk about index sorting, which is a new feature of Lucene, which was introduced in Lucene 4.3 back in May. And this feature has a lot of use cases. For example, you can use it to improve index compression, but the most exciting use case of this new feature is that it allows you to trade off index speed for search speed in a way that can dramatically improve your search latency. So I'm going to try to describe the way it works and how to use it. So in order to describe the way it works, I first need to give some reminders about the way a Lucene index works. So basically, a Lucene index is a collection of immutable segments, which are actually not fully mutable because we have one file which is used for deletion, which is actually a bit set, where you can turn bits off when you want to delete documents. But apart from this file, everything in the segment is immutable, and an index is a collection of segments. This means that if you want to add data, you need to add a new segment to your index, and in order for the number of segments to not grow too large in your index, there is a background process in your Lucene index which takes care of merging segments so that the number of segments in your index remains not too large, because otherwise search would become too slow. So something which is important to know regarding this architecture is that the order of segments in an index doesn't matter for search, and the order of documents in a segment doesn't matter. So I didn't mention it, but in a segment, documents that you index are stored sequentially. And for example, here I gave an example of an example for one segment which has two fields. So we have one ID field and one price field. And basically, these two segments that we are describing are the same. So the only difference is that documents are not stored in the same order. So for example, the ID field could be a stored field, while the price field could be a numeric doc values field, or the opposite, it doesn't matter. The important things to notice is that the order of documents inside the segment doesn't matter. So actually, the index of a document inside the segment is what we call a doc ID. So if you're familiar with Lucene, you probably already heard of doc IDs, and it's nothing more than the ordinal of a document inside the segment. So these doc IDs are dense, starting from 0 to the number of documents, the -1, that there are in the segment. And these doc IDs are actually used in the posting list in order to encode for the matching document. So for example, let's say that we have maybe a fashion shop on the web, and you want to make the content searchable for our users. And this is the way Lucene would encode for the fact that documents that talk about shoes are document 1, 3, 5, etc. So this is what we call a posting list, and it uses doc IDs, which are ordinals inside the segment. So now I'm going to talk about how Lucene does in order to find the top matching hits. So let's say that we are still looking for shoes, but we would like to get the most expensive shoes first. So the way it works is that Lucene will first create a priority queue of size 2, and then it will accumulate matching docs. So first, we'll create an empty priority queue, which will be empty, and then we'll visit every matching document, which are in green on the chart. So first, we visit doc 3. So the size of the priority queue is still under 2, so we can add it to the priority queue. Same for document 4. But then, when we visit document 20, we notice that the priority queue is already full. And priority queues are a very nice data structure, which can automatically overflow the list value so that they only store for the document, in this case, which will have the higher prices. So we keep on visiting documents, and when we visit the last document, we know that the documents which are stored in the priority queue are the ones which have the higher prices. So in that case, these are documents 9 and 31. So I use the IDs of the documents in order to identify them. Sorry. So what's the cost of collecting these documents? So it's very easy. It's the number of documents that you need to visit times the time it takes to overflow the priority queue in order to remove the list element, and the cost of this operation is logarithmic. This means that the cost of the collection is the number of matching documents times the logarithm of n, which is the number of top hits that you would like to get. This means that the more top hits you would like to collect, the more expensive this operation will be. So now we are going to do the same on a sorted index. So let's use just the same process. So starting with an empty priority queue and filling it with the matching document that we are visiting. And something, in that case, the index is sorted according to the price in a descending order. And something which is very important to notice is that the content of the priority queue doesn't change after we have visited n documents, n being the size we configured for the priority queue. This have very important implications because it means that first, you don't need to use a priority queue in order to collect documents. You could only use an array and fill it until it is full. And the second implication, which is very important, is that we don't need to collect every document in order to find the top matching hits. So for example, in that case, we only had to go until document 3, whereas there are 17 documents in this segment. So what is the cost of the collection this time? So we had to visit 2 documents, and we didn't have to use a priority queue. So the cost is way cheaper. And this is why index sorting, when used with early termination, can help you dramatically decrease your search latency. So, as I said, this can make search much faster, and it is first-time cache friendly. But of course, there are not only advantages, and in particular, for it to work, you need to have static ranks, meaning that you need to know when indexing which sort criteria you are going to use when searching. So this is not applicable to all use cases, especially if you want the sort order to depend on the query. So for example, if you are using TF-IDF in order to rank your result, the score of every document is going to depend on the query. So this is definitely not something you can sort your index at indexing time on. Then it requires the index to be sorted, okay? But maybe another issue that you could have is that it doesn't work for tasks that require visiting every document. This means that if you want to compute the total number of matches, or if you want to compute facets on your matches, this is not a feature that you will be able to use. But still, so one drawback that may sound like a big limitation is that it only works for static ranks, but actually static ranks are everywhere. So you have static ranks when you're working with graphs. So PageRank is an example. So PageRank can be an example of a static rank that you could use to sort your index. We talked about Twitter this morning. Twitter is a very good example as well because in that case, the rank is the timestamp of the tweets because you only want to give tweets by having the most recent tweets first. I gave a link to a Facebook paper about their search engine, which is very interesting because it's a very recent paper. I think it was published only last year. And they are talking about the way they use sorting according to a social rank in order to do early termination their indexes. And it's very easy to read, so if you have a few minutes to spend reading a paper, I definitely recommend reading this paper, and many more. For example, I know that SoundCloud has something which is very similar to Google's PageRank that they call Disco Rank, etc. So static ranks are everywhere. And even in the case that you don't want to sort exactly on your static rank, this is still something that you could use. So let's say, for example, that you configure your score to be the multiplication of a static rank with like the TF-IDF score. If you collect only twice the size of your priority queue results, you will already have a very good approximation of the top hits in your index, and you will still benefit for the dramatic speed increase of early termination. So, how can you use that with Lucene? So, something to notice that an index can't be kept sorted. The reason is that, as I said, segments are immutable, and if you wanted to keep our index sorted at all time, it would imply inserting documents inside segments, which is not something we can do because segments are immutable. So we need to find alternative approaches in order to work around that. And one first idea that we can have is to do the sorting offline. So the basic idea is, first, let's index our content as usual, then sort the index offline into a new index, and then search the sorted index using the early termination technique that we just described. So it's not a bad idea because the index will be fully sorted, meaning that you will be able to use early query termination. The only drawback is that it only works for static content, meaning that if you want to have an index where you want to be able to update or to add new documents, this is not something that you will be able to do. So, but still, how could it work? So first, so here is code. As you can see, it's very short. So index sorting is very easy to implement. So first, we are opening a directory using a directory reader as usual. And the interesting part is right after, because we are configuring a sorter, which basically describes the way the index should be sorted. So in that case, we are saying that we want to sort according to the price field, which is a numeric doc values field, and we want to sort it in descending order because ascending is equal to false. And then what we do is that we are basically creating a sorted view over our existing index. So this sorting view will expose everything as if the index was sorted, but it will be a bit slow because it will need to remap. Every time you will query the Lucene APIs, it will need to remap all doc IDs to new doc IDs and new doc IDs to old doc IDs, which can be a bit expensive if you want to use it for searching. However, it can be used for merging, because in the case of merging, every posting list, every stored field, etc., will be consumed only once. So the fact that it's view slow is not a big deal. So basically, what we are doing is that we first build this sorted view over the existing index, which is actually memory friendly. It tries to use as little memory as possible, and it's not too bad at doing that. Then we are opening an index writer on a new directory, which is different from the one we used in order to open our reader. And we are basically using add indexes in order to add the content of the sorted index into this directory. This means that if you start it again and open a directory reader over the directory where you put the sorted index, the index will be a raw Lucene index, which will be sorted and super fast to search. So that's it for offline sorting, but it's not really the solution we expected, because it's not that often that content doesn't change. I mean, if you are indexing archives that never change, it can be a good way to sort your indexes, but we would also like to be able to sort live content. So how can we do that? So first, since segments are... Okay, so first, in order to be able to do that online, one approach could be to sort segments independently. So this wouldn't require inserting data into existing segments, which are important, again, because segments are immutable. And collection could still be early terminated on a per segment basis. So let's try to see what we can do with that approach. So again, segments are immutable. This means that if we want to write a sorted segment, data needs to be sorted before we start writing the segments. So about Lucene segments, there are two kinds of segments that you can find in the Lucene index. The first kind of segments that you can find are segments that come from flush. This is when you add documents into the index writer buffer and then call commit, or if you reopen a reader from the index writer. So in these two use cases, the segments that will be created will be a flush segment. And the other kind of segments that can be created is a merge segment, which will be created when there are too many segments in the index, or when some segments are a very high ratio of deleted documents. So Lucene will try to merge them into new segments. It's kind of tricky to try to sort flush segments, because the way Lucene works is that it works part of the data, such as stored field and term vectors, on the fly, meaning that when you start adding a document, there will be some data which will be kept in the index writer memory, such as the posting list and the term dictionary, but stored field and term vectors will be directly written to disk. So if we wanted flush segment to be sorted, we would need to buffer all this data, and that would be very expensive. Okay, so now let's see what happens with merge segments. So actually, with merge segments, it would be pretty easy to sort segments when merging. The idea is that by default, when merging segments, Lucene has a list of segments that it needs to merge, and it will just concatenate these segments into a new segment with removing the deleted document. We could just do what we did for offline sorting, and when we get this list of segments, we could build a sorted view on top of it and write this sorted view as a new segment by passing it to segment merger. Actually, working this way is a good trade-off because when you run a search, most of the time it's not actually spent in flush segments, which are very small, but in merge segments, which are usually the large segments of your index. So taking a look at the Lucene index, it's very likely that your indexes look like that, meaning that you have a few very large segments, some middle-sized segments, and a lot of very small segments, which are flushed segments. So especially in a near real-time context, when you are reopening your index reader often, flush segments are very small, and it's not unlikely that merge segments are actually taking almost 99% of the size of your index. So again, this makes us confident that only being able to early terminate collection on merge segments is a right trade-off. So if you'd like to get more information about segment merging and the way it works and how Lucene looks like, how Lucene index looks like in terms of segment sizes, I recommend going to this link, which talks about it and is very interesting. So we implemented it, and it's called online sorting. The way it works is through a merge policy. So here is the way you could use it. So when instantiating a new index writer, you first need to create a new index writer configuration. And the only thing you need to do in order to do online sorting is to wrap your merge policy into a merge policy wrapper that we call sorting merge policy, which will take care of merging sorting the segments that need to be merged. And once this has been configured, there is nothing more you need to do. Just index document as usual, and your merge segment will end up being sorted. So now we have our sorting indexes. So in the case of offline sorting, they are free sorted, and in the case of online sorting, they are only sorted per segment. So how could you do early termination in both cases? So in the offline sorting case, it's very simple because the index is free sorted. So you just need to stop collecting documents after n matches have been visited. There is no proprietary key needed, and it's going to be super fast. Online sorting is going to be a bit slower, but still way, way, way faster than doing a standard search with Lucene. And the rules are the following. You should not do any early termination on flush segments, but as we saw, it's not an issue because flush segments are very small, so they are very fast to collect. But you can do early termination on merge segments. So there are two conditions that you can early terminate on. The first condition is that you already have visited n matches in the current segment, so you know that you don't need to visit more documents. And the second condition is that the current match that you are visiting is less than the least element of your priority queue because you already found better documents in the previous segment. So this is the second condition you can early terminate on. So how does it work code-wise? So here is the collector implementation. I removed the method. So for example, when you implement a collector, you need to implement stuff like set scorer. So I removed it because it's not related to early termination. But if we look only at the implementations of set next reader and collect, the only thing you need to do is first in set next reader, which is called every time Lucene will start visiting a new segment. First, you need to check whether the segment is sorted. So we have a utility method in sorting merge policy in order to check that. So because sorting merge policy takes care of adding some metadata to the segments that it writes in order to be able to check later on whether the segment is sorted or not. So this is what we are using in this collector, in set next reader, and we reset the count of collected documents. Then, in the collect method, which is called for every document that we are going to visit, so we first check if the reader is sorted, otherwise we need to collect it anyway. And if the reader is sorted, we check the number of collected documents. If it's greater than the number of matches we are interested in, we can only terminate. And if the current value that we are visiting is less than the value of the top of the priority queue, we can only terminate as well, because there won't be any document which has a higher value later in the index. And in order to terminate the collection, we just need to throw a collection terminated exception, which is an exception which has a specific handling in index searcher, and index searcher will immediately terminate collection on the segment that it is collecting. Okay, and that's it for index sorting. So if you have any questions, I'll try to answer them. Yes? So the question is it possible to early terminate on a per posting list basis? Is it correct?
Yes. Yes.
So what are you thinking about? Are you thinking about maybe something like or n queries? Okay, so if you have a static rank and you want to take into account TF-IDF into your score, something you can do is that you can configure Lucene so that your score is a multiplication of your static rank and your TF-IDF score. Okay? And then you can configure, for example, let's say that you want to collect the top 10 results. If you configure Lucene in order to collect the top 100 results per segment, it's very likely that you will have a very good approximation, especially if you make sure that the range of the values that your TF-IDF score can take is small compared to the range that your static rank, the values of your static rank can take. And it's very likely that you will have a very good approximation of your top results. The only thing you need to make sure that you need to collect more documents than the number of documents you are expecting to show to the users.
So the question was how replication works with merging segments. So as I said, you only publish a revision after you commit. So as long as segments are merged, nothing is and you don't commit, no new revision is published. If you're on a revision X and a number of merges happen, then that's the benefit of it. The client will only update the merged segment, not the intermediary segments.
The question is, if we have two equally possible static ranks, how do we do? The problem is that there is a contract in the Lucene APIs, is that when you have a doc-synum, which basically could be the result of a query, which will iterate over doc IDs. Doc IDs need to be emitted in order. This means that if you have two sort order in the same segment, at least one of them won't be in order, so this won't be compatible with the Lucene API. However, something that you can do, which is probably not as heavyweight as it may sound, is to index the content twice. Once for every sort order. So the question was, I have another use case for for index sorting, which is that I have, for example, one field which is sorted, which I used to sort, and I want to find results which are between M and P, for example. And you could use the fact that the index is sorted in order to make this query efficient. So it's true, because as I said, when the index is fully sorted, you don't need a priority queue anymore, which is where the costs come from when you are doing this kind of query with Lucene. So indeed, it could make this kind of queries much more efficient.
Okay, so the question was if we have already started to work on the other replication strategies, and I specifically mentioned peer-to-peer. So the answer is no, we haven't started. There is work that has been done, and there is a very nice paper which I guess it's very easy to find. It simulates BitTorrent-like replication. That's where I got the idea, so it's not my idea. But I invite you to work with us on that. So the question is if you need to replicate a large number of files, whether we see any problems with the replicator. So aside from this being HTTP and every file requires setting up an HTTP session, I don't see why it should matter much, because if you need to replicate 1 gigabyte of file or 100 smaller files, then it just means more connections to maintain, but I don't see any problems with the current code that will prevent you from doing that. So the question is if whether the bookkeeping that the replicator does on which revisions are replicated, are currently being replicated by other slaves, can be replicated by itself to other nodes. I would say yes, but I don't think that it makes much sense because the files do not reside on the other servers. So if you have two servers, one of them wants to serve files and you want to replicate its state to another server, and if A goes down, you want to continue replication from the other server, it needs to also have the files to serve. Okay, now if A went down, then there is no, well, I don't know if there is a lot of sense to replicate the state because clients will need to be directed. They will get an error. But sure, I mean, you can implement your own replicator which maintains the state, for example, in Zookeeper, and so all the nodes, well, first the masters replicate between themselves, and then. The question is whether we can use the HDFS directory for replication. HDFS directory is, I think, only in Solar, not in Lucene. HDFS is a different replication strategy because HDFS does replication itself, and this is a different replication because in HDFS you replicate every byte, or let's say every block that is being flushed. Now that might be very expensive because if, for example, you have your indexing node indexes a lot of documents, many merges go by, the index is rewritten 5 times, and now a client comes up and says, okay, I want to replicate. Then if you do HDFS replication, then it means all the merge segments are being replicated over and over while nobody needs them, because until you commit something to the index, no reader can see the commit or replication doesn't work with near real time. So until you commit something to the index, the readers don't need to see the updated version of the index. So I think that HDFS replication in that case will be slower. Well, depending on the app, but it might be. Okay, I think that we are over our time, so let's take more questions during.